Alright, David Ken here. In our last video, what we did was we talked about a mode of transportation that you could use to fall through the Earth and wind up on the other side. Using only the force of gravity, no external power source was needed. You could fall from one side to the other and wind up on the other side straight through the Earth in just 42 minutes. Okay, well this sounds pretty appealing. Ignoring the issues of being weightless for 43 minutes, 42 minutes, it certainly sounds promising to be able to reach the other side of the Earth that quickly. But what if you don't want to go directly across to the other side of the Earth? What if you want to go, say, New York to London or Sydney to Tokyo? Not through the Earth's center. What if you want to take a path like this? Is it still possible to fall through? Well, the answer is yes. How would this be different from falling straight through? Well, you wouldn't be weightless. Acceleration, if we put our little train car in here, acceleration is going to pull you, due to gravity, is going to pull you towards the center of the Earth, but you're also going to have a normal force due to the rail, which is supporting you and preventing you from falling through the tracks. So even though gravity is pulling you in towards the center, you're going to accelerate at a lower rate towards the center of your tube. Which means that you're not falling with the acceleration due to gravity, which means you're not in free fall. You will still have some acceleration, you still will feel some weight, which means you will be able to sit in your train car, even though it'll feel a bit like going over a hill at a high speed. You might feel your stomach contents rise a little bit at first when you first start moving, but you won't be in total free fall. You will still accelerate through to the center, and then decelerate to the other side. And again, if you don't hit the brakes, you'll just keep falling back and forth like this. So we know that it'll be a more pleasant ride than going straight through, because you'll have some weight. But how long would it take to roll from New York to LA, or from Sydney to Tokyo? To answer that question, we're going to have to look at some similar tools that we looked at last time. Here's the Earth again. And let's draw in that tunnel, like so. Here's the center of the Earth. And here's your train car. Now your train car is a distance x from the center of the Earth, and that's what we're going to use to determine the acceleration due to gravity. You're going to feel an acceleration due to gravity in the direction of the center of the Earth, but you're only going to have a net acceleration in the component of your direction of motion. Now, what x is and what this component is will depend on your distance from your equilibrium position, and we'll call that y. So what we have here is we have a right triangle. A right triangle with an angle in the center. We'll call that angle theta. Alright, so this one's going to be a little bit more complicated to set up, but actually we're going to find that it's not too bad. First off, we are able to calculate the acceleration due to gravity using the same formula that we developed in the other video, because it's really the same situation where you have a shell around the Earth, and you're really only affected by the inner shell, not the outer shell. So it's still the same formula from the last video, g equals negative 4/3 pi rho g x. But the problem is that g isn't your acceleration. G isn't your net acceleration. G is the acceleration due to gravity. So we also need to calculate your net acceleration, which is going to come from trigonometry. That net acceleration, a, is going to be the acceleration due to gravity times the sine of that angle theta. So we're going to have to work with that angle theta. We're going to have to be able to describe it in some way. Fortunately, we have a side and the hypotenuse of that triangle, which allows us to say that the sine of theta is equal to adjacent over hypotenuse. This gives us two important equations. 1, 2, that we're going to use to determine this time of travel. All right, so let's start with equation 1. Oh, here's equation 3. Let's start with equation 1, which is A equals G sine theta. Using equations 2 and 3, I know what sine of theta is, and I know what G is. And I can make those substitutions. This gives me negative 4/3 pi rho G x times sine of theta, which is y on x. Here's where something really cool happens. This x cancels with this x. And what I'm left with is negative 4/3 pi rho G y. Why is that important? Why is that y important? That y is important because it represents my displacement along this tunnel from the equilibrium position. The equilibrium position is right here in the center. And y is my displacement from it, which means that once again, my acceleration compared to my displacement from equilibrium is proportional and opposite. My acceleration is proportional to my displacement. My acceleration is opposite to my displacement. Therefore, again, this is simple harmonic motion. Because this is simple harmonic motion, we can again say that the acceleration is going to be equal to the angular frequency squared times the displacement from equilibrium. Now, I'm not going to be able to solve this in quite the same way because the acceleration depends on the angle that we're traveling through. In fact, the acceleration is related to this equation here. So I can make that substitution. And so I can say that negative 4/3 pi rho G y has to equal negative omega squared y. The negative signs cancel, but so do the y's. Which means 4/3 pi rho equals negative omega squared, or positive omega squared, excuse me. This is a significant result. I left out, 4/3. 4/3 pi rho G is equal to omega squared. This is a significant result because y has disappeared, which means that omega does not depend on how long this tunnel is. The value for y depends on the angle that you take through here, which determines the angle theta, but none of that shows up in this equation. This equation depends only, the angular frequency and therefore the period depend only on the density of the Earth. That's the only thing in here that could possibly vary. G is a constant throughout the universe as far as we're aware. 4/3 pi, that never changes. And the density of the Earth doesn't change either. Not in our assumptions anyway. Which means the period, or the time across, is the same. For all straight tunnels. And that's 42 minutes. I don't know, I find that that's an incredible result. What that means is that it takes 42 minutes to fall through the Earth in any direction. 42 minutes to go straight through, 32 minutes to go New York to London, 32 minutes to go New York to Tokyo, 42 minutes to go from your house to the grocery store via a tunnel through the Earth to the store, a straight tunnel. All right, so here's a challenge for you if you're up for it. It takes the same amount of time to go through every tunnel, but the tunnels, of course, are different lengths, which means you must be attaining different speeds. I'd like you to be able to find out if you can tell me what's the maximum speed you'll achieve in any of these possible tunnels in the Earth. I'll let you figure that one out, but I'll give you one hint. It's not going to be gravitational potential energy is equal to kinetic energy, mgh equals 1/2 mv squared. That's not going to be the solution. Because as you travel through the Earth, the acceleration due to gravity is changing significantly. So you're not going to be able to use this simplified equation for gravitational potential energy. This isn't going to work. You'll have to find another way. I'd love to see if you can figure it out. Let me know.